Okay, wonderful. So let's begin. First of all, I'd like to introduce myself. My name's Jade Hayes. I'm the Centre Manager for the Defence Data Research Centre. The DDRC is a transdisciplinary research centre focused on the socio-technical understanding and application of data science and AI for defence and beyond. We're funded by the Defence and Science Technology Laboratory, DSTL, and the Defence Artificial Intelligence Centre, DAKE. We're a centre led by the University of Exeter, supported by Liverpool, Surrey, and the Digital Catapult from London. I'd like to welcome Dr. Costa to our monthly Synthetic Data Workshop series. Before I ask him to introduce himself, I'd like to just mention a few housekeeping things. We're recording this session, which we'll then release later on to watch at your leisure. Cameras and microphones have been turned off, sorry, but I will turn them on. God, those reverse. But I will turn them on later on once Fabrizio gives me the signal. Feel free to pop your questions in the chat throughout or raise your hand at the end and I can turn on your camera and microphone where you'll be invited to introduce yourself and ask your question. Okay, so that's it from me. I'd like to hand over to Dr. Costa. Welcome and thank you.
Hi, thank you very much for having me. Okay, so hello everybody. I'm Fabrizio Costa. I'm a senior lecturer at University of Exeter. I work primarily in machine learning and in applications having to do with bioinformatics, but recently I've been very interested in the problem of generative AI and specifically how to quantify whether these generative models are any good. So without further ado, let me share the screen and let's start. So, close this. Fine. What are we going to talk about today? Here's the rough roadmap. I'm going to, first of all, motivate a choice of working primarily with data in terms of graphs or networks. I'm going to try and have a very brief overview of how can we process graphs using machine learning. And then we're going to look into what are generative systems, why do we actually need to measure the quality of these generative systems, and how can we actually do that. And then there's going to be a proposal for a quality measure and a proposal for a generative system that can be used also for the problem of generating graphs. So first of all, why graphs? Graphs can be seen as a sort of a universal data structure that's very useful for describing relational type of information. And so by using that, you can formulate lots of interesting problems, and you can create models that allow you to solve problems in applications such as transportation and logistics, power grids, network security, recommendation system, bioinformatic applications. Let's just go through some of those quickly. So for transportation and logistics, you can model roads, air routes, shipping lanes using graphs. Once you can do that, you can employ machine learning systems to optimize routes, predict congestions, and improve logistic planning. Regarding power grids, you can use graphs or networks to model the connections in the power grids and the utility networks. And then you can then use machine learning methods to enable predictions of failures or to optimize energy distribution and maintenance scheduling, for example. Regarding network security, graphs can be used to model network traffic patterns, and therefore you can use then machine learning systems to detect anomalies in these patterns, to detect potential security breaches and intrusion attempts. Everybody's familiar with recommendation systems, so graphs can be used to model relationships between users and items such as movies or consumer products. And so you can then use machine learning to create systems that can suggest which item a person or user should be interested next. And finally, this is closer to my heart. Graphs can be used in bioinformatics applications. You can use them to model molecules or proteins interaction networks. And so you can then use machine learning systems to predict molecular properties. You can predict drug target interactions. And you can use machine learning to generate novel drugs and to generate efficient synthesis pathways. So graphs, I posit, are very, very useful type of data that you might want to be able to manipulate and process with machine learning tools. So now, how can you do that? That's going to be a 2-slide introduction to how to process graphs using machine learning. There are 2 types of approaches. Mainly, they're known as graph neural networks and graph kernels. All right. So to keep a high-level idea about what's going on, in both cases, one might think about having a way to transform what is this nodes and edges, entities and relationships into a vector. So once you have a vector, so a sequence of numbers, then you can use standard machine learning algorithms, and all is good. Okay. So now the problem is, how do you do that? How do you go from graphs to vectors? So one approach that's offered by graph neural networks is to consider every node individually and then transform every node into a vector and then aggregate this information, having, for example, by summing everything up and having a final single vector that represents the entire graph. Now, this representation of the nodes are going to be adaptive and problem dependent. So how is the adaptation going to be computed? So here on the top right, you see a simple graph, and one can say, okay, let's look at this red node. This red node is connected to other nodes, and these other nodes are at different distances. So some of the nodes are at 1 hop away. So for example, this one here and the yellow here, and other nodes are at 2 hops away. So they're more distant. So these the information that can flow from distant nodes, has to pass a larger number of steps before reaching, in this case, specifically this red node. So what happens is that you can now formulate a predictor task where you're saying, okay, every time I have a node, this node has access to these immediate neighbors. I'm going to combine information that I can receive from those neighbors, either in simple ways. So for example, I take this representation, I just multiply it by a certain value. Okay, I have to learn what these values are, but that's going to be the simple transformation that I do. Then I sum it all up. I now have a single vector, and I combine it with the vector that I have for my own node, and that's going to be my new representation for the node. And this can be iterated at several steps for several layers of this network until I reach my final representation of a node. Once I have the final representation of all my nodes, I can sum them up. I have my final representation of the graph. I can have a more complicated type of processing. I could say that I want to be able to determine how important is one neighbor when I'm trying to incorporate its information. And so I'm going to have a function that's going to look at both my central node and my neighbor node, and it's going to decide on the basis of something that can be learned, how important is this extra node, okay? And so it will come up with a value that's going to be, between 0 and 1, and saying 0 is not important, ignore it, and 1 is very important, consider it. Okay, so these are attention-based mechanisms. Once again, this can be iterated layers by layers to get more complicated aggregation. And finally, the last step is saying I will have an entire arbitrary function that takes into account both my current node and the neighbor, and will decide what is the message that has to be incorporated every time. And so this can be an arbitrary neural network, and that's known as this generalized message passing architecture. Okay, so this is a very quick description of how we could use neural networks to take into account some attribute information that nodes can have and transform it in steps, aggregating information from the neighbors, and making sure that after we can take into account more and more distant contribution from different nodes, so that eventually we'll get a vector representation for the nodes and eventually a vector representation for the entire graph. Okay, so now we can go from graphs to vectors. The other approach is known as the graph kernel approach. There are two variants. One is implicit and one is explicit, but you can think about it, just to fix ideas, as an approach where you decide about a certain decomposition of the graph in terms of smaller, simpler subgraphs. Okay, so here in this picture, you see these are going to be small neighborhood graphs. Everything that you can reach with a small number of hops, 1 or 2 hops from every single node. So you obtain these fragments, and you could find a way to assign an identity to each type of fragment and to count when some fragments happen more than once. You count how many times certain fragments, like a triplet, how many times this triplet appears. And then you can have a way in this way to form a histogram. And that's a vector. That's, you have positions, you have values, how many times things have occurred, and that's a vector that you can use for subsequent computation. Okay, so now we have gone from the problem of having graphs to the problem of having vectors, and now we are asking ourselves, what are generative systems? So there's a very nice symmetric way with a classical problem of defining what a predictor or classical classifier is. So we start from there, then we say, so what's a classical classifier or discriminative system model is. So a discriminative system is a system that receives an input, a information, X, and outputs, decides what's the probability associated with a certain target value. Okay, in this case, here's a classifier that receives an input images and has to output a target that can be either a cat or dogs. Okay, what's a generative system is a system that, given a certain class, all cats or all dogs or faces or molecular graphs, has the problem of generating the X, the actual value of the instance that's associated with that specific target. Okay, so here's lots of examples how to generate variants of the Mona Lisa, generate variants of portraits, of plants, and so here, for example, of molecular graphs. How do you do that? So we've seen how you can transform a graph into a vector, and therefore you can use standard machine learning model to make a prediction of a class. But how do you do the generative step? So this is a non-exhaustive list of methods that are used to generate graphs under the deep learning framework. So the idea here is that you're going to have neural networks, and they can be organized in architectures ranging from what's known as variational autoencoders, generative adversarial networks, or GANs, normalizing flows, diffusion models, autoregressive models. So It's a recent and exploding domain in literature. Just to give a flavor to fixed ideas, I'm going to tell you about the autoregressive model. So here the idea is, suppose you are given a task to generate a graph. You can decompose the task in a series of steps. At any given step, your task is to generate a single new node and attach it to what you have generated before. So you start from generating a single node, not to be attached to anything. And the second step will be to generate a new node and attach it to the previous one. Then a third node attached to one of the two. Then you generate a fourth node, and then you now have to decide how to attach it to these subgraphs that you had already generated. So are you going to attach it to a single node, to two, to three? So this process of, first of all, encoding these graphs in a way that can be processed by machine learning, we've already seen it, with graph neural networks. You can always do that. You can convert it to a vector. And now you have a series of decisions that you have to do. And so that's a sort of a standard traditional approach where you have to model a probability distribution between the actions that you can do. Okay. And by doing that, you then generate a full graph, and the systems can be trained. So the right moves should be to generate one graph that you have in the training phase will receive a higher score than not. And so once you have the capacity to generate the graphs that you've seen in the training set, the idea is that now the systems can be used to generate more graphs, more than those that have been seen in the training set, okay, using the same principle. Okay. So now we're going to go on with a few extra questions. So the first thing is, why are we interested in generative models? So in general, the idea is that generative models can answer the question, can you please make more of something? And that has lots of interesting applications. One of the favorite application is that of oversampling minority classes. So here you see an example where there are more red instances than blue instances, and you would like to have a system that will generate new instances, maybe new red instances, but also many more blue instances, so that roughly you have the same amount. That's very important because discriminant systems can be fooled by highly unbalanced cases. So if you have a case where you have 99 examples to every single one of the other class, then a classifier would be 99% accurate if it just predicts the majority class. Okay, so you don't want that. Because this is one of those instances of problems that occur very often. For example, when you have anomalies detection, the anomaly will be very infrequent. When you have intrusions will be very infrequent with respect to normal activity. So that's an application case where there's a clear benefit. Another application is that when you have to generate instances which are not identifiable individuals from the training set. So that, for example, when you want to, you have medical records of patients and you want to generate data which is similar to those patients, but now they're not identifiable, and therefore you can develop your own learning algorithms with this generated data sets that would be useful on the real cases, but where no privacy has been broken. Another application case is that of generating instances which are sufficiently different from the original ones that are not being covered by patents, or they're just novel, and so they're useful and they're interesting. And finally, you really want to have a system that can generate stuff, because you can then, for example, drive an optimization problem where you have a specific objective and you say, okay, generate more, let's say, molecules, and now let's optimize for this interesting task that I have in my mind, this interesting objective. And so you want to have a system that allows you to sample these points in this space, but now these points, they have to be constructed generatively. So why are we interested in developing a good quality measure for assessing the quality of these generative models? Well, so there's two main reasons. One is, okay, I have for a specific domain or problem, I want to know which of these different generators is better. Maybe one is better for a certain type of instances than another. So I want to quantify that. I want to rank the different generators. But also internally, we want to have a way to, when we're developing a single generator, to find the best parameter set. And so once we have a quality measure, we can do that. Here's an example of the quality of face generation from the early 2014 to nowadays. And you see how progress has happened. So the problem is, how do we actually measure the quality of generative systems? Because while it's very easy to do that in a discriminative setting, so when we have to predict a class, and that's because we have access to the to some examples with the true target, and so we can simply compare and see how many times we get it right. But that is something we cannot do with newly generated instances. So we don't know what's the truth associated with each new generated instance. So traditionally, there have been different approaches. So the simplest one is simply to look at them and see whether they're any good. So with images, that's fine and easy. You can humans can look, especially the images we're interested in, and see whether they're any good, what's the quality of the images generated. Now with graphs, that's not so easy. So here's 3 examples of graphs which are all isomorphic. They're exactly the same graph. It's only that the layout is different. So for humans to look at graphs and see whether they're high quality, they're good, they're in fact even the same thing, it's very hard. Another approach was that to use statistics. So you can extract some measurements from those graphs, from the set of all the graphs which are produced. So for example, the degree distributions. You see every node and you see how many edges it has. And from the average number of edges should be the same between the original real dataset and the new dataset, the generated dataset. Could be other things, the average path length, and so on. Now this, of course, it's a bit of a coarse type of measures. It could be are people, I see here in the chat that people are having problem. Jade, do you have problems in hearing me?
No, I can hear you perfectly, and nothing's popping up in my meeting chat.
All right. Okay, fine. Let's crack on. Other quality measures are: is the generative systems capable to produce a large number of different graphs? It could be that it just produces the same entity over and over again. And also, is it different from the ones that we had in the original set? If it only produces copies, that's not going to be interesting. So people have gone from that type of measurements to this different idea, which is you transform your instances into vectors, or for graphs, or for images, you transform them into informative spaces in vectors where is important to understand whether 2 vectors are close to each other. Therefore, it would mean that the 2 underlying entities, images or graphs, they are similar in some sense. Okay, and so once you have that, you can now check for distributions overlap. So suppose you have your generated instances that form this distribution and your real instances that form this distribution here. So this is sort of a way to represent where there's a concentration of instances. And so ideally, you would want the 2 distributions to be perfectly overlapping. If that doesn't happen, you can compute two notions, the notion of precision and the notion of recall. So the notion of precision would be, well, I want to see whether the elements that I generate are any good. If they fall in the distribution of the real data. These empty circles here are not. They're outside of the distribution. So they're not high quality. Okay. Conversely, you could have the symmetric idea and you can ask, okay, if I consider only the real data, is the generator capable to generate and cover the entire distribution? These examples here are not covered by the red block. So our generator is not going to be able to generate them. Okay. And so there's a large part of the space which is not covered. So there are lots of things which we cannot access through the generator. So this is what these notions can be once we apply them to images, which is easier to visualize. So here you have 4 sets of images, A, B, C, D. And here you have a graph where you have these 2 measures represented along the 2 axes. So the vertical axis is the precision, the horizontal axis is the recall. So you have A that has a high precision but low recall, and D that has a low precision but high recall. And what that means is that these images in A, they're all very similar to each other. They don't cover the entire space. And these images here at the other extreme, they are very different. They cover, different background, different hats and whatnot. But it's not high quality. Okay, you can see how the images are not high quality. So this can be formalized. There can be this notion of similarity expressed as distances. So here, don't worry too much about this, but the notion is, well, I can take a instance that's generated. I can look at the neighbors. I can put a threshold. Let's say I consider 5 nearest neighbor. I see what's the distance between my instance and the 5th nearest neighbor. And I'm going to see whether I can capture some of the real instances within this threshold distance. If that happens, I'm happy. I count as yes, I have been able to generate an instance which is close enough to a real instance. Okay. And so now you can formalize this and you have this way to express a number that says how much is the precision, how much is the recall of your generator. Now, that this definition has a few drawbacks. It relies on the notion of computing meaningful distances or densities, which in high-dimensional spaces is a very difficult thing. We'll just see it in a second. The scoring function will be very happy with identical copies if this were the output of a generator, while we said that perhaps in many applications that's not something that we would like. So our measure should not score high a generator that produces copies. Also, this is a bit more subtle, but there could be telltales about the instances that are generated that make them very distinguishable from the original one. And also, in this case, we should give a high score. So here is a simple example that shows that looking at exact distances in very high dimensional spaces might not be that meaningful. So this is the distribution of the distances in a cube of unit size when it has 2 dimension, 3 dimension, 100 dimension, 10,000 dimension. And what happens is you can see that all the possible pairwise distances of randomly distributed points, they start to concentrate. It's a known effect of high dimensional cases. The actual value of the distance starts becoming less meaningful. The other problem here is the near copies. So you could have a generator that, yes, can generate very interesting, realistic images, but they're all the same, or very interesting molecules, but they're all the same. Okay, so you don't want that. Yeah. Finally, the telltale, that's a more interesting subtle case. So it could be that the generator is capable to generate something that on the whole is acceptable. So you do have, for example, this is a nice, very high quality image of a person, but there could be certain subtle things that generator cannot do. So in this case, it's well known that image generators have problems with the number of digits or drawing hands. So the number of digits are always different than what it should be. And so that's a small detail out of the whole image, but you would always be perfectly capable to distinguish when this happens. And so to distinguish the generated image from the original image. In the case of molecule here, you see these two sets. If you look at the degree distribution or the neighborhoods, they're the same. So every atom has the same neighbors, but the difference is that in this case, for example, you have cycles, and here you don't have cycles. So at the end of going around, you will find yourself back at the origin, and here that doesn't happen. So it's a single feature, but that could tell the difference between the generated instances and the original instances. So for this, we propose a notion of quality metric that, in fact, combines different quality metrics so that we can take into account all those issues and all these things that we want and desire to be sensitive to. So we call those four things: the quality, the usefulness, the similarity, and the indistinguishability. So the first two are more quality-based, and the last two are more similarity-based. So the key insight in this proposal is to try to use what we know how to do, which is how to measure whether discriminant models, classifiers, are good at what they do or not. So we're going to define all those measures using classifiers outputs. Okay, so this will result in something which is less affected by these problems with high dimensionality, and it's also more issues. More sample efficient. So here's the quality. So I'll just give information about the concept behind it rather than giving you formulas. So how do you establish whether the generated images are of a high quality? And here is the reasoning. You use the real instances to train a classifier. You then use the generated instances to train a similar classifier of the same type. And now you test both of them on the same instances, real instances. Now you can ask yourself, what's the ratio between how accurate these two models are? If the ratio is roughly 1, then that means that the generated instances were of a high quality, because you've been able to create a model that was very accurate on the real instances. So it could really discriminate cats and dogs, but it was only trained on the generated images. This is not very good images, so I don't expect here the model to be of a high quality. So anything that's far from 1, that would be a lower quality. So now onto the concept of usefulness. Now, usefulness is this notion of are we actually creating copies? So to do that, we have to introduce an auxiliary concept, that of the learning curve. What the learning curve is a representation, is a quantification of how much is your classifier improving for a specific task if you train it on more and more data. So if you only train it on 20 instances or 200 or 1000 instances, you're going to have a different accuracy. Okay. So now the question that you can ask is, okay, what happens if I consider training an instant classifier with 200 examples, but now I generate a few hundred examples starting from that training set. Now I compare a classifier that's now trained on the union of the data, so the original training set plus the generated set, and something that would happen with real data, so the original data, and a real few hundreds of instances that are real instances coming from the real distribution. And now you can compare what happens for the accuracy of the classifier. If you are only generating examples which are just a copy of the original data, it's not that you are having a classifier trained on several hundreds of instances. It's equivalently going to have the same performance as if it was just trained on the original data. Because that's, having 2 copies, 3 copies of the same is not going to make the classifier be any better. Okay, so again, the ratio here will tell you how much useful and innovative material has been generated. For the similarity notion, that's going to be on the same type as we've seen for decision recall. But here the idea is simpler. There's no distance threshold that's going to be considered. And so the idea is as follows. You consider real instances, you consider the generated instances in the same space, and now you look at neighborhoods, okay, of both sets. Okay, you consider, in the case here, you have blue and red instances, they overlap perfectly. And so every time you consider a neighborhood, you expect the number of neighbors to be from both sets in an equal ratio, 50-50. If the 2 sets don't overlap, when you consider neighborhoods, there's going to be only neighbors of one type or the other. Okay, so you can measure this discrepancy by a notion of entropy, and you can see whether it's true that these neighborhoods are homogeneous or not. Okay, so that gives you this notion of similarity. As for the notion of indistinguishability, here's the problem is, can I identify telltales? So here's just an illustration to say that you have 2 features that make the 2 sets indistinguishable. So if you were to look at these 2 sets of points from above, you couldn't be able to distinguish them. But then there exists one feature, the vertical feature, that allows you to perfectly discriminate them. Okay, so now you can extend that to have hundreds of features that are indistinguishable, but there are few features that perhaps would allow to the 2 sets to be discriminated. So how do you measure that? Well, you can say that the instances that belong to the original class, the real class, are class 0. The ones that are generated are class 1. Now you have a binary problem. Now you can train a classifier and see whether it can classify correctly. If it's not performing well, then there are no telltales, and then these 2 sets are indistinguishable. So something which is inversely proportional to the accuracy, so the error, is actually a direct measure of the indistinguishability. Okay, so now we have these 4 concepts. Yeah, so we have the quality, the usefulness, the similarity, and the indistinguishability. And I propose to put them together in such a way that it could be more informative, and it could help us diagnose what's the quality or what are the properties of generative systems. I propose to, first of all, put together the quality and the usefulness. So if we can get something that's useful for discriminating our original problem, and if we can get material which has high quality, can be used to train a discriminating system. So these 2 notions can be averaged together. The same, we can average together the indistinguishability and the similarity. And now we can form 2 concepts which can be of use. The compatibility concept, which is just both have to be true. They have to be high quality and high similarity. And that would yield the notion of how compatible is the generated material with the original one. So we can substitute it, we would get the same result. But also we can develop the notion of creativity. So that would be instead the ratio between the quality and the similarity. And here the idea is that if we can get something of high quality, but using instances which are not highly similar, they are dissimilar, they are new, then that's a very good thing to have. All right. Now we're just adding the +1 so that if the similarity is 0, this doesn't just go very high. All right. So you have to be high quality. It's irrelevant to be very creative, but then generate rubbish that is not useful at all for your original task. Okay. So it will always depend on the quality of what you generate. The quality is 0, then there's no creativity there. So if you have a high quality and they are also not very similar, the instances you generate from the original ones, you do get a high score in creativity. Okay, so now you have these two measures. You can plot these two measures, the creativity and the compatibility, and you can identify these regions. So here you obtain lines where you fix one of the two, for example, the Q, and then you range over S and vice versa. And so this tells you that, if you increase the creativity given a fixed, if you are more and more dissimilar given a fixed quality, then you are increasing the creativity. So here are a few examples. Now we don't have much time to go into very many details about these, but these are artificial examples where one can manipulate the quality of the generator artificially. Okay, and then you can see what happens to those measures, and you can see whether it reflects some intuitions that one might have. So here, for example, the notion is to have more and more noise in the quality of the generator so that it becomes less and less good. But to do that, what we do is we simply change randomly the target associated to every instance. So sometimes you have positive instances which are labeled negative and negative that are labeled positive. So the quality of the instances, the similarity of these instances to the original dataset remains perfect, but the quality and the usefulness goes down. Okay, so that behaves as expected. So here, what you can try to do is to increase the ratio of copies. You substitute the instances which are generated with exact copies from the training set. So you see how the similarity starts lower, and then eventually it becomes perfect because we have just replaced everything with identical copy, but the usefulness goes down. That behaves as expected. Here's the so-called mode collapse. That's what happened when you remove entire clusters of points in the generated sample. And so what happens is that, of course, everything decreases, specifically the quality decreases, the similarity decreases. So we are not covering the possible space, so similarity goes down. And finally, here we have this indistinguishability. So here we have only one feature out of all the possible features of the instances that becomes increasingly more and more different. Okay, and so here what you can see is that the quality would fight, because a classifier can use its ability to not consider irrelevant features or features which are useful to discriminate things, but the indistinguishability would decrease. So finally, I have the last 15 minutes. I will give you an introduction on an approach that we've been developing here on how to create a generative system that would perform well according to this novel quality criteria. So the desired characteristics of this generative system is that it has to be based on very simple principles so that it can work with very few examples. So desired characteristic, especially when we have this minority sampling applications. It has to be able to work with variable data densities. So to deal with outliers, it has to be able to recognize where outliers are and not take those into account. We don't want to sample generate lots of outliers. And it has to work with high dimensional domains and graphs. So there's these two main ideas. One is, how do we get the good instances, which are not outliers? And one is, how do we remain close to what's called a manifold where data exists? Okay. So the proposal is very simple and works as follows. It makes use of the notion of mutual nearest neighbors. So what a mutual nearest neighbor is for A, the three mutual neighbors are these instances, and these are mutual neighbors because if you consider that these instances in turn, they have A within their three nearest neighbors. Okay, so C is not a mutual neighbor of A because while C has A within its three nearest neighbors, A does not have C within its three nearest neighbors. Okay, so that is a way to identify outliers. Very simple way to identify outliers. And then there's this notion of how can we capture the relationship between instances so that we remain within the manifold. And that's very simple. We perform the following operation. We say, okay, we consider the neighbors of A, B, and now we consider the neighbor of B, let's say B prime. And now we consider the relationship between B prime and B, which is computed as the difference between the two. And now we're going to apply the same relation. We're going to apply the same relation that exists to A. And that will allow us to compute A prime. And that's it. That's all that there is to it. Okay. So interestingly, this also can be used for graphs. I'll show you how. So this is what happens when you have a simple artificial case. You have normal distributions, and now you want to generate new instances using this notion. So here, only with one mutual nearest neighbor, just a pathological case, just to see what happens in this very specific case. Now, when you have a generic, let's say, 10 nearest neighbor, you see what happens here. Areas which are very dense will receive lots of instances that will be generated, but also you'll see how things will not be overlapping excessively on the existing data. They will try to fill the space between data. Okay, so it will generate novel data. Here's a concrete example on the famous MNIST dataset. That's a dataset of handwritten digits. These are real instances. These are generated instances. You can see here how you can discriminate between the real instances and their so different classes of the real instances. This is just binarized, like all odd numbers are one class, or even numbers are a different class. And so you can separate them. And the same decision boundary can be obtained by using only generated instances, very similar to the original decision boundary. You see here how we can reach a very high quality, a very high indistinguishability, a very high similarity, but still not a great utility. So if I add these instances to the original training set, I go from 77 to 78 accuracy, so not a big improvement. If I had added the same amount of data, but real data, I would have got 85 accuracy, so a clear jump from 77. Okay, so this helps us diagnose that the quality of the generator could be improved. Okay, so here's another case where instead we have a mixture of distributions, but we have two classes. Okay, we have the blue and red. There are just two different classes, and so now we're asking, can we have not covering the whole data space, but only concentrating on those instances which are very close to the decision boundary? And would that be any useful? So if you do that, so here's the application to also a MNIST data set, but in this case is one-dimensional. The interesting thing here is that when you do that, and so you only sample on the decision boundary, you increase significantly the utility, because you are adding the system to discriminate, and you're getting things which are less similar than before, because they're only covering a smaller part of the domain. So that seems to be an interesting way to say, given the definition of quality, that's a good direction where I can go to improve, let's say, the creativity of the system. And so finally, we have the application of these things to the graph domain. So here, the notion is, can we use the same principle to generate new graphs? And so can we take two graphs, find what's the relationship between them, the difference between them? In this case, for example, is this fluorine atom here. Can we apply it to a new neighbor and obtain a variant that includes the reason why these were different? Okay, so you can do that. This is the guy that's been added. And so you can try to evaluate it empirically. You can try and evaluate it with other, to see how it does against other generators, these deep neural network generators. And here you will see that the proposal scores very high, higher than most of the other generators, not as high as the best of these deep neural network generators. All right, I'll leave some time for questions. I just leave with a few questions. How can we do to integrate complex domain-specific constraints in this whole approach? For graphs, how do we integrate attributes? So you've seen how we can exchange smaller subgraphs, but what about all the real valued attributes that nodes have? And how to best discover meaningful decompositions, meaningful fragmentations in interesting parts, so that these operations are more semantically relevant. All right, I'll stop here. So I'll be glad to take Jade questions.
Thank you so much, Fabrizio. That was really deep and insightful. So we have a bit of time for maybe 1 to 2 questions if anybody had any burning questions. Andrew, thank you for raising your hand. Please feel free to turn on your camera. It's enabled now, and maybe briefly introduce yourself for those that may not know you.
Sure. Thanks, Fabrizio. I'm Andrew. I'm one of the graduate research assistants at DDRC on synthetic data. You mentioned you've got several different definitions for measuring your synthetic data. Was it creativity and quality and similar to that? Do you have set mathematical definitions for those measures, or are they kind of flexible to the use case?
Sorry, so these notions that we talked here, yeah?
Yeah, thanks.
So for each one of those, I gave these intuitive notions in terms of what happens when you train a classifier. You can have the ratio of the accuracies. So indeed, these are measures that are obtained empirically, modeling what happens when you train classifiers on those generated and original instances. So there's a lot of noise. There's a lot of standard deviation there is not going to be. So here you see the result of these measures. These bars are standard deviation. Okay, sure. So they give you numerical results with some certainty. It depends how many experiments you do.
Okay, so they're all based on different ways that the classifier has performed.
Yes.
Great, thank you. Thanks.
And Fabrizio, we have a comment in the chat.
Yes, so these methods rely on training robust classifiers, and there are conditions when this would be difficult, and how would be this dealt with? Indeed, so it's you have to choose how you wanna on which hill you wanna die. So the other approaches are based on a definition, a meaningful definition of a metric space. So if you have a wrong definition of the metric space, so how do you say that two graphs are similar or close by? So if that's not accurate, then all your measures are fail. Your densities are going to be failing. Here we are saying it's much easier, rather than talk about densities, to talk about classifiers and discriminative boundaries. Okay, so that should improve the robustness of the approach. Of course, if you cannot make any classifier that has any capacity to correctly classify your instances, even your original instances, your true instances, your real instances, then you do have a problem. Yes.
I'm just curious, Fabrizio, is there any way to overcome that, or is it just, an issue from the offset that can't be overcome?
So no, so the point being that if you don't have a discriminative problem that you can tackle successfully, probably whatever you're going to generate is not going to be useful for in practice. So unless you can use those instances to perform meaningful tasks, so can we discriminate between the attacks or the non-attacks? If you can never be able to discriminate that, then indeed generating new instances, then you don't know, according to this approach, you wouldn't know if you're generating anything that's good or not. But yeah, well, hopefully you have approaches that can solve the problems you're interested in.
Indeed. We have a raised hand. Please feel free to turn on your camera and introduce yourself. We've got 3 minutes left. Hi.
Hi, sorry, I asked the question about the classifiers in the chat, just quick follow on from that. So I guess I would be interested to hear your thoughts on if you're using this generated synthetic data to create a classifier, and you wanted it to improve the classifier. Do you have any thoughts on like how this would sort of feed back into itself? Just anything on that topic?
Well, that's exactly the point, isn't it? So you would use a generator to, so what I've shown is one way to do this generation is by using this principle. So that's independent of the classifier. You generate data and then you see how good it is. So in this case, you've generated more data here, more digits. And you see, well, it has, if you train a classifier on top of it, you went from 77 to 78. So you've improved a little bit, not too much. The utility is not great. Now, perhaps you have to change something in your generator or in your data to increase the quality. But now you have a way to measure the quality. So you know if you're going the right direction or not.
Okay, thank you.
Yes.